So it's my great pleasure today to welcome this week's speaker, David Garcia. David started out with an undergraduate degree in computer engineering in Madrid, then moved to a master's in computer science in Zurich, and then a PhD in what I guess was already computational social science with a PhD on collective emotions in online communities. There then followed an academic journey across a number of cities and institutions, Zurich, Graz, visiting professorships in Barcelona, Vienna, and he's now in Konstanz, in Germany, at the University of Konstanz, in the department, interestingly, of politics and public administration, where he holds a chair in social and behavioral data science. He's going to speak to us today about from digital traces to generative agents, and I'm really looking forward to this because one of the things we haven't looked at all in the series so far is any kind of social interaction or socially motivated cognition, which is a huge gap in the context of understanding human cognition overall. So without further ado, over to you, David.
Thank you. Thank you very much, Ulrike. Yeah, it's a pleasure to talk today about some of our latest research. I'll present a couple of papers for which we just have preprints out. And just a note, if you want to see the slides, you see the URL there, thegarcia.eu/GenAI 2025, for anyone that wants to look up anything I say. And yes, I want to introduce my lab a little bit. I mean, I call it the Social Data Science Lab, even though true that my position is social and behavioral data science. But my feelings is that almost anything social, of course, is also behavioral. And I studied first the human behavior from digital traces, what we used to call computational social science. But often I was missing the systemic perspective, because we had all of this messy data. That's how I moved into more complexity science, what I was doing in Vienna. And now I'm noticing that the methods we're developing and the tools we do require a bit of a different methodological approach that we call responsible AI. I will talk more about that, but basically there's been a journey that already Rick mentioned. It's been a very interdisciplinary one, as you said. I'm a computer scientist by training. I did my PhD actually in a management and economics department. Then my first lab was in a medical university. Then I was in a computer science department, and I'm in a political science department. So I'm a undisciplined scientist. And in my lab, it's similar. So, for example, Giordano is a physicist, Segun is a computer scientist, Taihi is a political scientist, Alina and Hannah are psychologists, Apex is a communication scientist, and Emma is physicist and computer scientist. And we try to collaborate with each other. We don't have our single papers. We do big collaborative projects. That's why we are located in several places where I still have projects. I'm here in Uni Constance, but still some of my lab members are in Vienna and in Graz. And we try first to explain human emotions with computational models and computational methods. In particular, trying to make the methods understand and respect human emotions. And the running example I will use for why we need generative agents is actually one of the emotions. Then we have the emerging topics of information disorder, so from disinformation sharing to hate speech to privacy problems in online platforms, and also again trying to use at least the complexity science perspective, was the network aspect, for example, in this phenomena, and also trying to explain polarization and inequality, especially through digital traces and having models that explain their emergence and their origins. And today I'm going to present first a bit of my journey towards trying to explain social collective behavior, in particular online, and some of the gaps or struggles I had in my experience, the things we're missing, and why those are calling for a new modeling approach where we can introduce large language models or other generative models to try to simulate these kind of collective behaviors. We have one paper first where we studied how we can grow social networks with these kind of generative agents and what are their properties. And this has also brought us to think about generative agents. Now, one of the latest buzzwords is AI agents, and what happens in society, we have like LLMs doing things for us. And so the topic of collective behavior from generative agents is more than just using it for science, is what happens in society when we use them. So I show you basically 2 research projects on collective behavior of generative agents. So first, one of my biggest topics, and the one I did my thesis on, was on collective emotions in online platforms. And I started trying to explain collective behavior from agent-based models. So the idea that you can model the behavior of individuals and the interaction with each other with some minimal ingredients to try to explain what ingredients are necessary or sufficient to generate some collective behavior. And so the typical example here, what you see on the right, is that we're modeling, for example, the dynamics of emotions. Often we try to do it with empirical data on experiments. I'll show you an example in a minute. But the idea is that we have a theory that is written as code that we can simulate or that we can analyze mathematically and see under which conditions or what are the necessary components for collective behavior to emerge. For example, it could be a collective emotion defined as a collective emotional state shared by a large number of people at the same time. And this collective emotional state doesn't need to be only unimodal. You can have several emotions at the same time. Some people being excited, some people being sad, for example. But the idea is that there is a large amount of people. What is large is always a philosophical question, but it's not just 1 or 2 people. It's a large crowd. It is shared, meaning that there is some sort of coupling between people. It's not just experience in isolation, and it's at the same time, meaning that there's a synchronicity. It's not at different moments in time, each individual is that there's something together. And in my previous work, we studied this through digital traces, in particular analyzing the text of a lot of social media text to identify the situations of collective emotions, thinking that there's some that happen spontaneously, for example, they emerge in a community or in a platform, or in others that can be externally triggered but still are different than emotions experienced in isolation. And what I show you there on the left is an example of a study where we did that. I got lots of tweets from France over time and analyzed emotional expression in French tweets around the terrorist attacks that happened in 2015, and there we can see like a huge spike of negative emotions, and in particular a decay of that takes a few days to go back to neutral, and that shows that these are just not very spontaneous emotional reactions individually, but that there is also some sort of memory in the system that makes it survive for some time. I mean, the second panel is more one of the consequences of that sometimes these emotions are correlated with things like prosocial behavior or social orientation, and that's in a different time scale. The users that were in the collective emotion kind of talk differently about helping others for a long period of time. And part of my work was trying to explain these kind of spikes. How long do they last? Which emotions trigger differently? Who is being involved? How does the network explain these kind of patterns? And in general, it's this idea of like bridging the micro gap, like this level here, to the macro gap of explaining some collective behavior, generating it with a simulation. And there was always a bit of a struggle on having models where the behavior of individuals is not a fantasy. And so it's very easy to make a computational model you simulate with some basic principles of human behavior, but this only is useful for analysis of collective behavior if those principles, those microdynamics, are supported by some kind of evidence. And the model is basically a tool to bridge different levels of behavior from individuals to collectives. In complexity science, learning from physics and so on, there's a tendency to simplify things and try to make an analytic argument on the model, on what is necessary, but whether that is actually happening empirically sometimes is left as an open question. And I always wanted to have this agent microdynamics in a way that we can analyze in the individual level of behavior. So, for example, for collective emotions, already a while ago, we did some experiments where we showed threats, emotionally charged threats to individuals, and we had a formulation of emotion dynamics. This is an example is the change in valence, like positivity or negativity of an emotion over time, is something like a relaxation to a baseline, and it gets excited by communication with a few parameters. Here has 3 parameters, and then some sort of stochastic factor. And we set some experiments to do that, with some conditions, but without a precise hypothesis testing, more with the idea to try to make measurements as precise as possible of some of these parameters so that we can use those measurements. And that's the calibration, the idea that you measure a parameter and then you can use that elsewhere in your theory, in your model. So this was a bit of a conflict with a typical experiment in psychology, where you really want to test a hypothesis, sometimes trying to be something as surprising as possible that then fits into a larger theory. But here it was more for actually trying to represent the behavior we observe in the experiment as well as possible with some quantitative expression of that, and then use that into a larger model. So that's why it didn't fit very well the typical psychological discussion. It was something more about what can we get from this data rather than do we get or not a thing we were a priori looking for. And this was something that we used then later in this, for example, the model about the collective emotion in Paris and so on. However, there's always a lot of assumptions about simplifications in these kind of models, and also in the experiments, in which, for example, we simplify interaction to just a variable or 2. I mean, here was like the positivity or negativity of the thread, or the level of arousal or of excitation of the content that the agent read. And also the dynamics of the agent are simplified to just as few variables as possible, like valence and arousal were the case today. And so you always have to transform everything to a very small set of numbers, simply because you cannot get infinite data for these kind of things. And that was first one of the main problems, especially simplifying the interaction to just this set of numbers that very often require, for example, assumptions about perfect communication online, the idea that people don't make errors when they understand what people say. I mean, here everybody understands the emotion perfectly of what is being said, and there's no room for error or variability there. When you have the models of opinions, people get to know the opinions of others. I mean, there's a noise is just a random thing. It's never modeled as something that, for example, can vary across individuals. And very often, these models especially are motivated to propose some sort of policies or interventions. And that's one of the biggest promises of complexity science. Since the 80s, they were telling us that we're going to have these models of agents and particles and networks, and they're going to help us to make better policies. And up to now, like 40 years later, there's very, very few exceptions where that has actually informed policy making. And my feeling is because of all of these simplifying assumptions are very helpful as academic exercises to explain things, but they become too simplifying when you actually want to turn that into a policy. For example, a typical thing is that you simulate a policy where you have an assumption about the effect of a treatment at the individual level and how that percolates in a network. And usually the treatments are not that simple. There's a lot of, for example, heterogeneity of effects, some contextual factor of effects is never always going to be the same. And we might have also other factors that explain different types of behavior of individuals that might not be just one has a higher or lower threshold, or is more central or less central, but we could actually have identities and beliefs and things that are basically not what we can model with the harmful variables. So this paradigm of trying to measure and calibrate things with experiments for service, put them in the agent-based model and make a prediction of collective behavior became, to me, too limiting to be able to propose a policy. I would put my hand on the fire to say this is going to make the world a better place, or even to be able to make a more precise prediction of what's going to be the effect rather than just increases or decreases some kind of outcome. And that's what was bringing me into the idea of trying to use generative agents, and that's the idea that we can have a large language model driving the behavior of an agent and try to use them to simplify some of these assumptions of agent-based models, especially for online interaction, because the LLMs are producing text, and when we model online textual interaction, we're having now a model for exactly the modality. And there is some work going in this direction. I mean, the first one I saw is this famous paper from Stanford, where they test some generative agents in a small simulation of a small town, and then they do some anecdotal observations, how the agents are able to move around and talk to each other and make like a party and so on. So it's a nice proof of concept that you can put LLMs to do things and interact with each other. And then the idea was getting a bit more serious into trying to simulate actual large-scale online systems. And there's this paper by Pete Thornburg and Chris Bell and colleagues, where they simulate an online social media platform where they give a prompt to each agent being an LLM with some information on the identity of the person sampled from a survey. And then you can evaluate if you change the feed algorithm, how is that going to influence, for example, the toxicity of discussions. And that's, I think, these are interesting ideas. Perhaps we don't need to replace everything with an LLM, but the LLM helps us to make perhaps more reasoned assumptions in the things we don't want to assume anything on. So, for example, in an agent-based model, very often you say like, so the typical question I was getting, what is the role of race in your emotion simulation? Like, I have no idea. Therefore, you ignore it, you don't model it. And that feels wrong. So we can perhaps have better priors by using all of the information that these models have basically learned from, and then see if we can interpolate things we don't understand by trying to have a more realistic simulator in which, of course, there's still a lot of development to make sure that the LLMs represent what they're supposed to represent, but at least to be able to not ignore all of these features of heterogeneity and more complexity than with just few equations that ignore everything else. And we're trying to do some of that right now. We started an AU project, by the way. It's called What If. We're trying to simulate online platforms. I think this is a collaboration with communication scientists where they are collecting data from donations, where you can take out your data from Facebook and answer some questionnaires, and we're using that to test and validate LLMs that will not be a whole replacement of agent dynamics, but some kind of a verbalization of agent dynamics that help to, for example, pilot interventions in the same medium as the agents, as text, for example, a warning on misinformation or an intervention when agents are too toxic. And then instead of having this kind of conceptual interventions or policies in the agent-based model, now we have something that can be translated more clearly into an application scenario, and hopefully, with some partners, we actually get to test some of these. And of course, replacing agents, replacing people with a chatbot is not the idea. No, what we want is to have better interpolation of the behavior of people in these models of collective behavior. So I want to show you an example of what we started doing on this, because we learned a few things I think we never thought about on how to model the behavior of humans, trying to reproduce, in particular, online social networks. That was our first base, and this is something that you might hear very often from network scientists, is that the very basic building block of online social networks is that there's some degree distributions, like the number of followers of a person tends to follow a power law distribution, meaning that you have the probability of finding a person with a number of followers follows this density function, that you have a decreasing power with a lambda, with an exponent of something like 2 minus 2. And this is a very typical stylized fact of networks. When you're looking at these kind of directed social networks and very heterogeneous kind of lives of nodes and users, you end up having these extreme fat tails and large variance of number of nodes. And we were wondering, if we put LLMs to connect with each other in a simulated social network, do we get these basic observations we get from data from empirical social networks as a first building block? Like, what if we simulate a network? What if we want to simulate then discussions and interactions? But let's start with just the structure of the network. Will it look more or less similar on this basic observation? Just a comment, not all networks have these kind of properties, but some do, and especially like the number of followers or the attention that accumulates on a person without the person necessarily building the links is one of the cases that tend to follow these kind of distributions. And often, especially network scientists and computer and complexity scientists, are too excited about this, and they don't explain why it matters. let me tell you two reasons why I think this matters a lot. One is that when you have a distribution like this one, you say, aha, it's just probability of finding a degree, it decays with a function of minus something. The variance of the sample, if you take a sample, a finite sample from this, the variance of the sample grows with sample size. So you take a platform with 1,000 users, and the mean might be the same, but the variance grows. If you take a platform with 1,000,000 users, the variance also grows. And it's an interesting property, like the heterogeneity, when the kind of extreme values grow with the size of the system. And it's not like a typical sampling. We have a normal distribution, and the extreme values don't only grow sub-exponentially, so to speak, with the size of the system. Here, they really grow proportionally to the size of the system. And the second property of this kind of networks, when you have these very degree heterogeneities or extreme heterogeneities, is that they don't have a thing called an epidemic threshold, meaning that if there is some sort of outbreak, the expected lifetime of the outbreak is actually tending to infinity. Like it never really dies out, because if it reaches a particular critical size, it always manages to reach one of these high degree nodes and stay alive. So there's also interesting properties for disease spreading, that when you have these networks, actually they explain some surprising behaviors online. I mean, I just saw this example from one paper that shows one of these networks, but it's recurrent. I mean, the statistics are tricky to test this, but overall, in particular, for like the number of followers of a person, is a recurrent fact. And we try to simulate this with this generative agents idea. And so what we did is that we took a number of generative agents, and basically one by one, we put them into the social network, and we tell them this prompt. No, you enter a virtual social network. You are tasked with connecting to exactly n individuals. So that's a parameter we use, like a number of friends. And then we show them a list of people, of other users, with the number of friends. I mean, we change this a couple of conditions, but basically you see something more or less like this list here, where the agent sees the name of the other nodes and the number of friends, the degree they have so far. So this is inspired in many network growth models, where every agent enter into the network one by one, and then they are tasked to connect to some number of agents as a simplification, and they see something like the degree of agents. So now the links are generated by the LLM. The LLM replies with, I want to connect to user A, I want to connect to user E. And then we construct the network and keep on growing it, and based on what LLM is basically telling us. So we simulate, if we take one of these networks, will we get the same kind of degree distribution as we see empirically? So here we're using basically GPT 3.5, but this is something that you can reproduce with basically any LLM smart enough. And the first thing we noticed was not a success all of a sudden. No? We simulated this, and showing the degrees, like the number of friends of each agent and the names. And we got a network like this one here, this hub and spoke network. This is a network where the variance in degrees is actually more extreme than in an empirical social network. You remember that plot that I showed you with a slope of -2? Basically, the slope here is more extreme. Like there's almost no nodes, or almost all nodes have a degree 1, almost nothing with a degree in the middle, and one node with a huge degree, or very few nodes with an extremely high degree. And this is not the same as this power law or scale-free distribution. So we were interested in like, it's not working. So it doesn't look like what people would do. And so we tried, and we said, okay, let's remove the degree information on the neighbors. They just see their names, and let's connect them to their neighbors without knowing how many friends they have. You get a list of who to connect to. We simulated that, removing the degree information, and now we got a network that looked a little bit more like the empirical one. It was, you can see now, it looks more like a line. The slope is not the right one, but it looked like pretty skewed. And like, okay, it looks surprisingly, removing the number of the degrees of the nodes looks more similar to real data than the other one. But we learned a few things about these simulations with generative agents. And here, when we look at this, there's some correlation between the age of the node, like when it entered, and the degree it has, but it's not very strong. And in these models, we know that there's quite a strong correlation between the degree of the node and the age. And we discovered that the reason why we have this kind of heterogeneity in the network, despite the nodes not knowing any degree of other nodes, not knowing the number of friends when they enter, is because there's a hidden Zipf's law. In Zipf's law in language, we also have one of these power laws for words. And even if we use random users' names, they also follow Zipf's law. And the LLM, as a language model, has a prior on these tokens. Even if they are completely random, they still follow Zipf's law. And the fact that we ask them to say the name of the other agent creates this a priori inequality in probability of saying the names. So friending a user X is not the same as saying I friend user X, because the X is a token that has this prior. And even if we use like completely random sets of tokens there or letters, they still have this embedded heterogeneity. So we noticed that the language is a problem. Large language models are language models in the end, they are not network models. And so we discovered that sometimes you need to reshuffle the names of things to be able to destroy these kind of priors on tokens. And we tried with that. So we renamed the nodes in every iteration. So we kept the IDs basically, but just the token associated with every node was different. And when we do that with the degree information, now we get something, and this looks very similar as this kind of growth of a network as you are connecting people to each other with this degree distribution that now you see this is like log, like the plot I showed you earlier, is very similar to the empirical one. And then when we remove the degree information with this reshuffling of names, then we get what we would expect a random network where the degree heterogeneity is very narrow, is much narrower. I mean, this is not log transformed here, the degree. So you don't have this high variance in the number of friends. So, I mean, we use this as the kind of the null feature of social networks, a power law degree distribution, and we show we can reproduce that, but only if we consider that these are not behavioral tokens, these are linguistic tokens. And in the future, when we're trying to do this, we're going to try to include tokens that capture, for example, liking something or retweeting something rather than saying, I like this, because the verbalization, so to speak, is problematic. I mean, imagine that you're making an experiment with people, and instead of them liking something, you make them type, I like it, or verbalize it. It makes sense that it's going to distort the outcome. So here it's pretty clear, given that the models are language models. And it was a starting point for us, to see, okay, it makes sense. We can simulate kind of the growth of the network. We analyze individual nodes and what is the probability that they connect to nodes of different degrees. Actually, here on the left, you just see like different cases with different sizes and how we're getting this kind of heterogeneous degree distribution. And the cool thing is that then we can look at the individual agent and see what happens when they are exposed to different degrees and see that the probability of connecting grows kind of linearly, not with the quadratic when you cumulative with that. So I think Steve is raising his hand. Should we pick
Yeah,
questions?
thanks for clarification.
Yeah.
I don't understand the issue of like how do you rename a node and what does the LLM do? I mean, is the LLM kind of saying, "Oh, I want to be friends with Jane or Magda"?
Yeah.
Is that what happens?
Yeah, so these names are basically strings of characters,
Sure.
and they don't mean anything
Right.
to us. But when we're doing this, what we do is that we just rename with another string of characters every node at every iteration. So when they connect to something, if they say a different name, it doesn't really matter because it is the name that corresponds to that node, and the degree is the corresponding name.
So why rename it? That's
we
what
rename it because of this, because when we don't rename things, we still have this heterogeneity and probabilities of them saying the name a priori because they follow Zipf's law. So we have already a heterogeneity of probability that they connect to someone just because their name happens to be on the higher probability range of Zipf's law.
Oh, so the LLM doesn't know when it's renamed what the
Yeah, so we rename it. The LLM has no idea that we rename it. It's just, and we rename it with a completely new character string,
Okay.
just to destroy that prior probability of connecting just because the node was lucky to get a string that is favored by Zipf's law.
Oh, I see. Okay, thank you.
So yeah, we thought, these are random strings. Of course, we thought there's going to be no prior, but yeah, still Zipf's law still applies because there's like subword token frequencies applies to even random strings. Yeah. Good. Did that help? Other questions? No? Okay. Then I'll continue. Yeah, this was tricky. It took some network science and some NLP or linguistics at least to understand what was going on. And where I was, yeah. So I was telling you that also when you analyze the individual agent, and that's a feature of this, it doesn't have to be a full simulation. You still can single out an agent and show different combinations of degrees and test if there is this idea of preferential attachment, that the nodes are more likely to connect to nodes with higher degree. And it's a very precise kind of preferential attachment that creates these kind of distributions in particular. So also, and there's something I'm going to come to in a minute, simulating the individual agent is also useful to understand the system here. And I wanted, now to show you the most exciting part now, because when analyzing this, we also came across the situation that we have a lot of things in society where we're using AI agents or like LLMs to interact with other people, and the idea is that this is going to happen more and more. So you are seeing every few weeks some big platforms start collaborating with OpenAI or whatnot to try to start having LLMs. And we were just talking earlier with Ulrike, like Zoom now has another LLM embedded. And of course, there's part of just hot air in these applications, but some of them, they're promising things that might happen in society, like having ChatGPT in your iPhone, and then when you say to your iPhone, I want a nice dinner reservation tonight, then it books for you. It talks to the chatbot of 1,000 different restaurants and books the best one for you. And the idea is that this could happen in a lot of things, like you're looking for an insurance, and instead of you browsing through a million options, you have a chatbot, you talk with it about your preferences, and then talks with the chatbots of insurance companies until you find the best one. So the idea of having this chief of staff to try to outsource to large language models or to chatbots everything that we don't really want to do in society. And some of these situations are for example, building on coordination. Some others might be building on competition, like the reservation might not be competition, but the healthcare might be a situation of a negotiation. And if we think about all of the chatbots, like being independent from each other, sounds okay. But when we think that this is a system and maybe the chatbots are also talking with each other, and there could be norms that makes maybe the system more efficient or find a better solution for everyone, but there could also be systemic risks in the sense that if all of the agents synchronize, that could be dangerous. And a typical example where we see that is in the stock market, where you have trading agents, and the idea is that sometimes, at least up to some more recent regulations, sometimes trading bots could synchronize for some dumb reason and all sell something, and then the price of security will collapse just because the chatbot synchronized. So they can create instabilities also if they happen to synchronize, even if it is for reading notes, basically, as an input. And we wanted to study this. And in particular, I wanted to see how large is a group that this kind of AI chatbots can produce, in the sense of like having some arbitrary coordination on anything where there is no ground truth, there's no better or worse option. Like how large can there be a group that agrees on something completely arbitrary? And there's an analogy of this actually across species, and is the idea of this Dunbar scaling. And is that, especially across species of mammals or social animals, you see that the cognitive abilities of animals correlate or are positively related to the average group size of different species. I think this is the plot that Robin Dunbar did 25 years ago, where he noticed that the group size of different species was scaling with the relative size of the neocortex to the rest of the brain, and actually created the prediction for humans that then, of course, there's some evidence of humans making these spontaneous groups of something about 150 to 200 people that then actually relates to also the number of contacts that you remember and people you trust. And this is, for example, the idea why office floors tend to be at most 200 people, because if it's more than those 200 people, you won't really recognize everyone. And then you will see people you don't know in an office floor, and you cannot predict very well their behavior on some arbitrary norms, and creates, for example, distrust, like you're going to think that they're stealing your lunch. Oh, Ian has a question. So we pick also the question now?
Hi, David. Can I just
Yes.
ask a quick clarifying thing?
Yes.
So, of course, I'm aware of this work, but I'm just thinking now, based on your previous results and just thinking more about the literature, is average group size really a good measure? I mean, if you look at human groups, it's probably more of a power law distribution. And if I think of like the types of groups that I typically study, it's also a sort of power law or exponential type distribution. In which case, maybe we should never have been using average group size. It should be more something about the group size distribution.
Yeah, good point. So here is, of course, trying to use the average. I think in general for humans nowadays in a modern society, what you talk about is the average number of contacts of a person. There's no group size anymore simply because we're not tribes separated from each other. And there you, of course, have a distribution. Even Robin Dunbar made his own survey of how many friends people have on Facebook or on other platforms, and then you see people with thousands of contacts too. So, of course, I think in reality there is a distribution. My thought here is more than the actual average, is the limit for finding a spontaneous coordination without a clear decision-making mechanism, like representation or laws or things like that, without written rules. So more than trying to say what is the average group size, actually trying to see what is the limit for a spontaneous coordination of a group. And then is when you see that humans don't get to spontaneously coordinate on arbitrary sizes when you are having this kind of face-to-face offline interaction. There's a number of limits. And the idea here for Dunbar was also that there's a cognitive limit. You need to remember people, you need to be able to talk to people, remember their identity. And then it's not, I don't think it's about the average, it's actually how hard it is to get or to find a very large group.
Thank you.
Thanks. I mean, we can talk more about that. I think there's time for discussion later. Let me continue, because there's a bit of a stretch between this group size and coordination that I want to explain. And I'm curious about your thoughts, because I wanted to see where AI agents lay here and where LLMs lay there, in different types of LLMs for AI agents, different families. And in particular, one thing that Dunbar is saying is that it is the linguistic or the communication abilities of humans that make us be a bit above that line than other species. And I wanted to say, okay, now we have language models, we can measure the linguistic ability. How does the linguistic ability actually explain this? And the idea is, and now I'm taking an inspiration from you, Ian. So we have the problem sometimes of coordination, and is a subset of opinion dynamics where opinions don't really matter which one you have, if it's A or B. What matters is that the whole group is taking the same decision, and there's no right answer. But when the group separates, then it might, for example, have a danger for a predator, or might have problems to find food. So this is the idea of coordination, that there's no real exchange of useful information besides where is the group going, and that you have some situations in which you might have a critical group size, after which, if it's too large, then you will have some natural fission of the group, and then have it separated into just two groups because they can afford basically this separation. And that was a bit the idea, the approaching path towards this measurement of group size on LLMs. Seeing how large can we get in terms of creating an agreement for a consensus, and then relate that to the average or to the maximal group size, not even the average one. How we did this with another simulation, like what I said before, we put LLM agents to talk with each other. We take a group size of n interacting agents, and they start with a random opinion, let's say between X and Y, two arbitrary options that there is no argumentation of why one is better than the other. They are just simply going left or right without any actual presence of information. And then for each agent, we show the opinions of all of the other agents in the group, so they see everything. And then we see like the name of every other agent. Again, there's some reshuffling here from what we learned, also reshuffling of names of opinions from what we learned from our network simulations before. And then we just make them be sentences like, so for example, like agent A, we show the opinions of all others, and it's like, what is your opinion now? Then we record that, and when we show it in the next iteration to all the other agents, we show the opinion that each agent said in the previous iteration. And so when I started setting these simulations, I thought, there's no reason why any of these chatbots will ever comply to this. There's no argumentation of why X is better than Y. So they will say one of the two options are random, maybe one has a bias or not because of the prior, but again, we'll reshuffle and we destroy that. So there's no reason why they would reach consensus. And actually, we don't even restrict it to X and Y. If they say P, we also record that they just stick to X and Y naturally from the properties of the model, and they don't have to coordinate at all. There's no utility. We don't tell them you have to agree. They say like, what do you say now? And first, when starting some simulations, first we notice that some models can reach consensus and others not. You don't see much here, but this is for 50 agents. We're simulating this scenario, and some models do what I was predicting, that like Llama 3 or GPT 3.5, kind of the smaller, cheaper models, they don't reach consensus. So this is a number that goes between 0 and 1. 1 is when all agents agree, and 0 is when it's 50-50 split. And this is based on 5 simulations. Some agents don't really reach consensus, and some others were reaching consensus every time we were simulating for 50 agents, in particular the most expensive models like Claude 3 and GPT-4. So first, it's not like all models reach consensus and some not. Some of them seem to reach consensus, and then is where I thought, okay, now we can try to measure this critical group size. No, like let's try to find how large can a group be to maintain consensus, or basically when can we have the small group small enough to have consensus in one of these cheaper models, and how large can it get to be? And so before doing that, we started analyzing how the representative agent basically reacts to a number of opinions of other agents. So when we're showing the mixture of opinions of others, we can measure this collective opinion as basically how many are on one side or another. Again, that kind of definition with 50-50 being 0, everyone on option A being -1, and everybody on option B being +1. And we can see the adoption probability, so the probability that the LLM says the opinion corresponding to 1 in the next iteration, or here will be the probability towards the opposite opinion. There's only two options. And this is for different models, and again, a size of 50 as an example. You see these typical S-curves, and some models have steeper S-curves than others. Like the cheaper models have flatter S-curves, and other models have steeper curves. And actually, we can tell from this S-curve, we can model it with one parameter only, that is the beta of the shape of the S-curve, and measure that as a majority force. When the beta is very steep, it's telling us that the majority force is very strong. So if you are here in the middle, just a little majority on one side or the other makes you flip, makes the LLM flip on that majority. But in these flat cases here, it's not that strong. No? Here you can have a situation with still quite a strong majority, and the model doesn't have 100% chance, because it only has like 80% chance or so to flip. So there's situations when it's not that strong. We can parameterize that, and we call that beta, the majority force of an LLM. And first of all, here's a few of the models. And the beta grows with the linguistic abilities of models. We notice that models that are able to do better in a language understanding benchmark have higher betas. But the interesting thing is that we can increment the size of the group, and then we notice that betas start to go down, so the majority force gets weaker and weaker in larger groups. And there's this critical value of beta that below 1, the majority force is not strong enough to create a consensus, and above 1, it still maintains the consensus. So we're able to tell already from this analysis of the beta that some models can have consensus, and we can break them if we make the group sizes too large. So we did some complexity science there, because actually we can apply one of these models of spins, the icing model, which is something that I never managed to apply myself very well in the case of emotions and online platforms, but here I managed. The idea is that we can simulate these agents as a big particle with different atoms that have their own spins, and they're coupled with each other depending on these majority forces and whatnot. And when we change the temperature or the size of the system, or the size of the number of particles, it makes it harder for it to magnetize. So basically, every object has some non-zero probability of becoming magnetic at any temperature, but it's extremely low. And when you decrease the temperature and make it particular way, there's this Curie-Weiss model from physics, in which you see that when you are increasing the size of the system, the time for it to reach consensus when you are in the broken non-consensus part grows really fast, basically exponentially, because in these cases it's only by chance that you manage to get the agents to agree. But when you have a group small enough, then it's not that fast. It's actually very fast. It's not that slow. It's actually much faster to reach that consensus. So there's basically a linear part and then an exponentially growing part. This is in a log scale. So there's this breaking point kind of here in the middle that actually from the analysis of beta, we can find what it is. And to be able to say when the group size is too large for an LLM to be able to reach consensus in these agent simulations. I mean, there's some funny math involved there, but it was one of the few cases where actually for me, one of these magnetic models has applied to one of the systems that I have analyzed. And in particular, here in gray is the prediction from this physics model, and in red, what we get with GPT-4, which actually follows it pretty well. So now we can measure this critical group size when there's a change of qualitative shape of this function. And now we get that plot that I was always looking for, that was to see this critical group size, which again is not an average, but more like a maximal size, as a function of the linguistic abilities of models, is of course kind of a proxy for cognitive abilities, but more following what Dunbar was proposing of language in a critical factor. And for many models, we see that they're lying on the same line, also with humans being there. I mean, humans also have a particular benchmark value in this MMLU, which is not 100%, we do make errors. And GPT-4, for example, 4.0 is close there. There is some kind of line, but there's some models, and in particular, the most expensive ones, 4 Turbo and 3.5 Sonnet, that we haven't managed to break. Here we're simulating 1,000 agents talking with each other for a very long time, and they always find consensus. So actually, we notice that some models are able to coordinate at a scale that goes beyond what we would predict from the same scaling of humans and other models. So something is happening there. We have some kind of special coordination abilities from some large language models, and that brings some concerns. Could this create unexpected behavior when you're having a lot of LLMs in society? Could it create systemic risks? Could it create synchronization that you don't want to have? And this idea of like some sort of locality of group sizes that you see in species and even in society across humans changes when you have LLMs, and perhaps you have millions of LLMs talking with each other. You are used to something when humans interact with each other, but these LLMs might be working differently and create some collective behaviors we don't see with humans, as this spontaneous synchronization they have here on a very arbitrary decision. And yeah, so this was what I wanted to show you today. And my idea, I want to improve agent-based modeling with LLMs. We started by trying to simulate these kind of social network structures, but then from that, we started trying to measure these kind of group sizes as a measurement of, or consensus scale as a measurement of group size, to test this idea that perhaps we're having, first of all, a scale between different elements, and also perhaps some synchronize or coordinate at a scale larger than what humans can produce. I mean, in the future, I want to work more also on using LLMs to simulate online platforms and seeing what happens there, what kind of collective behaviors. But I'm starting to notice that it's also important to study LLM agents in themselves, because they're starting to appear in our society. So even if they don't have to reproduce people, just the fact that they're starting to be used is a topic worth researching. And well, I'm looking forward to the discussion. If you want to learn more, I'm in my website, I'm in Blue Sky. Thank you very much for listening to me.